Hey everybody. Sorry we can't be together today for class, but hopefully this video will take care of business and you'll be able to carry on without a beat. So let's get started with our joke of the day, because I know you love joke of the day. So why should you never use a dull pencil? Because it's pointless. Good one, good one, good one. Okay. I know some people hate math, but you've got to admit, decimals do have a point. I love these. These are awesome. Okay, so let's get into section 1.4, complex numbers. We already started it, and I just want to rehash a couple of things that we had mentioned before we move on with what we're going to talk about today. So imaginary numbers, we talked about this, that they are the square roots of negative numbers. We said that before we knew how to take the square root of a number, we knew how to simplify square roots, but when there was a negative underneath the square root, we weren't quite sure what to do with it. But now we know that when we have a square root of a -1, that is an I. And we've also learned that if we take that I and we square it, and we square the other side, when you take the square root of a number and you square it, meaning it times itself, when you multiply a root times itself, you will get the number that's underneath. So this I squared will simply be a -1. So here are the two definitions that we need to keep in mind. We talked about all these higher powers of I, and honestly, I don't have that stuff memorized, like the -1 and the negative I and all that kind of stuff. These are the two that I definitely know, and then I build everything else off of that. So what this does is it allows us to simplify our radicals. Say, for instance, we've got a square root of a -8. This is no longer a 1, it's an actual number, like maybe a 9 or maybe a 15. And we need to simplify that radical. We said that our product rule will allow us to say that when we have two numbers that are being multiplied underneath the radical, that's what this is, a -1 times an A, then we can split that radical up. That's what the product rule says. I'm going to split it up as the square root of that -1 and the square root of that A, because now I know that the square root of a -1 is just an I. So this is just an I times the square root of A, and that allows us to take a shortcut that says, when I have the square root of a negative number, like we see here, as soon as you see the negative number underneath the radical, that means take the I out of the radical and deal with the number that's underneath. Either take the square root of that number or simplify that radical, but the idea is as soon as you see a negative, take an I out. And we said that this allows us to evaluate and makes evaluations a little bit easier. So we had taken a look at an example, and I just want to rehash the example one more time just to catch us all up to speed before I move on. And the example that we had looked at said that we were going to evaluate a square root of a -49. And we said that when we see that square root of a -49, that's the same thing as saying, well, I have a -1 times 49 underneath that radical, and the product rule says that I can split that up as the square root of a -1 and the square root of 49. I now know that the square root of a -1 is just an I, and I know that the square root of 49 is a 7. And we had discussed that this I acting like a variable, you don't ever write this, you always write the X in the back, the variable goes in the back. And right now the I is acting like a variable, so I'll write it as a 7I. And we had discussed before that you don't necessarily have to go through all these intermediate steps. I showed the intermediate steps to show why you're allowed to take the shortcut that says, I can start with this question. As soon as I see that negative, I can take the I out of there, leading me to this, and I can deal with the square root of 49 being a 7. So I could go straight from the question directly down to the answer without all these intermediate steps because of the product rule being in play and that definition of the square root of a -1. So now let's take this and let's expand on it and do a few more examples because it does become a little bit more complex. Let's say, for example, that I need to simplify and let's say, for instance, I want to simplify the square root of a -100 times the square root of a -81. Now, previously, our product rule said that we could multiply those two together. The product rule said you can start with things that are underneath a radical and split them up as long as they're being multiplied. If they're multiplied, you can split the multiplication up to two separate radicals, or you can start with two separate radicals and bring them together. So according to that, I should be able to do this and multiply the two together underneath one big radical, and then a -100 times a -81 would be a +8100, And then I can take the square root of that positive 8100, and I'm asking myself, what would I multiply by itself to be an 8100? Well, that's just a 90. And that's all well and good, except for the fact that that ignores that you had negatives underneath the radical. So if instead I would look at this negative underneath the radical and I would immediately take care of that, then that's going to affect my answer. Because here, when I see that negative, that tells me I'm going to take an I out of there. And I'm going to do the same thing here. I'm going to take an I out of that one. Now at this point, we all know that the square root of 100 is 10, so this is a 10i. And we also know that the square root of 81 is 9, so this is a 9i. But then at this point, 10 times 9 will be a 90, and I times I will be an I squared. And I squared, remember, as soon as you see I squared, you should be thinking negative 1. So this is a 90 times a negative 1, which is actually a negative 90. That is different than what we got over here, because this ignored the fact that we had negatives underneath that radical. Now technically, I could say a negative 90 times a negative 90 will give me a positive 8100. But there wasn't anything in this process that kind of indicated I need to pay attention to the fact that that is going to be a negative 90. So you really don't want to go through that process. And the tip is, if you're confused about, well, wait, the product rule said I could do that. Well, the tip is this. As soon as you see a negative underneath the radical, immediately take care of that negative and take that I out of there. And that will alleviate any of the problems that you could incur by not dealing with that. So let's try one more. And we are going to again simplify. So this time, let's take a square root of a negative 5 times the square root of a negative 10. Well, once again, we've just learned that as soon as you see a negative underneath the radical, deal with that. Take that I out of there. And we'll take the I out of this one. And so now I know that I can multiply those two i's together because they're acting like variables right now. And I times I will be an I squared. I can also take care of the square root of 5 times the square root of 10, that I squared in the back. And I know that I squared is a negative 1. So really I have a square root of 5 times the square root of 10, all multiplied to a negative 1, which essentially means I'm just going to put that negative out front. Now remember, that product rule said again that I can start with things that are separated and put them together as long as it's multiplication. So I can put the 5 and the 10 underneath the radical, and at that point, remember, I'm looking for perfect squares or pairs. Perfect squares are numbers that you can find the square root of. I don't know the square root of 5, and I don't know the square root of 10, but if I had a pair that would create a perfect square, and I could take one of that pair out, it would dissolve the other one. So here, I know that 10 is 5 times 2. Now I have a pair of 5s, and I can take one of those pair out, and that dissolves the other one. So I'm left with a 5 outside the radical, 2 underneath the radical, and the negative out front because that I squared was a negative 1. And that's as simplified as that radical will get. Now, like I said, this allows us to evaluate. So let's say I have a 4i squared minus a 2i to the third. Well, I don't know about you, but as soon as I see that I squared, I immediately start thinking negative 1. So I'm going to go ahead and turn this into that negative 1. And I do know that 4 times a negative 1 is going to be a negative 4. But I got to deal with this I to the third back here. Here's where I was saying all those patterns with the repeating every set of 4, I don't know those patterns. I just generate it because I know that that I to the third is going to be the same thing as an I squared times an I. And I do know that this I squared right here is going to be a negative 1. And now I know that a negative 2 times a negative 1 will be a positive 2. And remember, I acts like a variable until you see I squared. So right now it's acting like an x. It's acting like a variable. And I cannot put these two together, so I'm stuck. And that's as good as that one will get. Now this is what we call a complex number. Everything that we've dealt with so far has really just been like a simple imaginary number here, simple imaginary number here. They haven't been complex because we didn't have these two strange pieces being put together. Complex numbers are exactly that. They are complex. And complex numbers have what we call a standard form. And the standard form looks like what you see right down here. Notice this looks very much like what we have up here. So we have our imaginary part back here. And we've got our real part right here. It's what I call a mathematical mullet. Your standard form is a mathematical mullet. Back in the 80s, we had our mullets. The girls didn't wear mullets, but guys wore mullets, and that was where the hair up front was short, had all this long hair in the back. That was the mullet. And we used to call it business in the front, party in the back, so that you could look like a businessman when you needed to in the front, and then you could have your party in the back at nighttime. Anyway, so this is your mathematical mullet. You've got your real part in the front, you've got your imaginary part in the back. So business in the front, party in the back, mathematical mullet. Now, your complex number, when that A becomes 0, when this part, the real part, becomes a 0, all you're left with is an imaginary number. So that BI is an imaginary number. And basically that is just simply illustrating that when we talked about sets of numbers before, I told you guys that everything you could think of at that point in time was going to be a real number. Well, we can think beyond that now. Now we can get into complex numbers. That is the main category as a complex number. It's almost like the room would be a complex number. The grouping would be complex numbers. So within the main group of a complex number, you could separate it out and you could say, well, we could have real numbers within our complex numbers. And then remember all these boxes that I used, and within our real numbers, we said that we could have our rational numbers that could be written as fractions, we could have our irrational numbers that cannot be written as fractions. Within our rational numbers, we could have integers, we could have whole numbers, we could have natural numbers, but that would be all of our real numbers as one of the subgroups of these complex numbers. The other subgroup of the complex numbers is going to be these imaginary numbers, and when you put those two together, it creates the main group of complex numbers. Now, you can have equal complex numbers. This, quite frankly, is something that I feel is very intuitive. I feel like it's common sense, but every book that I have ever seen feels a need to mention it and illustrate it, so I'll go ahead and do that, although I don't think this is going to blow your mind. And basically what it says is I have a complex number right here, and I have a complex number right here. These two complex numbers are going to be equal if and only if. What would it take for this complex number and this complex number to be the same? Well, I think everybody understands that it would take for these two parts to be the same and these two parts to be the same. So they're going to be equal complex numbers if the real parts are the same, A and C are equal, and the imaginary parts are the same, and the B and the D are equal. If you've got that, then clearly you would have equal complex numbers. So there you go. Now, complex numbers can operate just like your real numbers can. In other words, there are operations that you can do with your real numbers: add, subtract, multiply, and divide. You can do that with complex numbers as well. So we're going to start off with adding and subtracting these complex numbers. And it sounds like it's difficult because we're dealing with complex numbers, but it's actually very easy because we just need to remember that I acts like a variable until you see I squared. And when you see I squared, suddenly you substitute a -1 in there. But otherwise treat it exactly like you would if it was a variable. So in my examples, I'm going to add or subtract each. And let's start with this. Let's start with a 13 minus 2i, that's a 13, not a b, plus a -5 plus 6i. Remember, I acts like a variable until you see I squared. So if it's acting like a variable, like an x, that would be like saying 13 minus 2x plus a negative 5 plus a 6x. Well, what do? Exactly, you combine up your like terms. So I'm going to combine up this 13 plus this negative 5, combine those, and I'm going to combine up those imaginary parts, the negative 2i plus the 6i. Well, what is 13 plus negative 5? Sure, it's 8. What is negative 2i plus 6i? I is acting like a variable right now, so it's just a 4i. Can I put these two together since I is acting like a variable? No, sure can't. Is that in standard form? Is that mathematical model with the real in the front and the imaginary in the back, the business in the front, the party in the back? Yeah, I got my business in the front, the party in the back. There's my standard form. And that is how you add your complex numbers. Now let's take a look at subtracting a complex number. Actually, I need more room than this. We'll go ahead and erase it. Here we go. Now, when I go to solve this one, I don't know about you, but one thing is just glaring at me, and that's that negative underneath the square root. Hopefully it's glaring at you as well. I'm going to fix that first, and at this point we all know that that simply means take an I out of there. Now, once I take that I out, it's looking a whole lot better, but I'm noticing, wait a minute, this square root here, I know how to simplify that. I know I'm going to look for a perfect square or a pair, and I'm going to break down that 18. 18 is 9 times 2, so I'm going to separate that out. And I know that the square root of 9 is 3, so I'm going to take the square root of that 9 out of there, and I'll be left with 8 plus 3i square root of 2 minus a 4 plus 3i square root of 2. And now that's looking a whole lot like what we had before. So I'm going to combine up the real parts, combine up the imaginary parts. The only problem is that this is a subtraction problem, but we know that if this I was an x, we would just simply distribute that negative through the second parentheses and turn it back into an addition problem. So that's what I'm going to do. I'm going to distribute the negative through. And when I do, I'll have 8 plus 3i squared root of 2 plus, now I'm distributing the negative through. Now I can combine up all the real parts and combine up all the imaginary parts. So I'll say 8 plus a negative 4. And then I'll combine up the imaginary parts. 3i squared root of 2 minus another 3i squared root of 2. Well, if I take a 3i squared root of 2 and I take all of them out, I got nothing left there. They cancel out completely. And I know that an 8 plus a negative 4 is simply a 4. So it's possible to start with a complex number, and once you do all these mathematical manipulations and operations with them, you can end up with a real number. It's very possible for that to happen. Just because you start with a complex number doesn't mean that you have to end with a complex number. So, now let's take a look at multiplying complex numbers. We've added, we subtracted. Now let's see what happens when we multiply. Again, sounds very difficult, but it's not that hard because all you need to remember is that I acts like a variable until you see I squared. When you see I squared, then you're going to turn it into a negative 1. So let's take a look at, again, some examples. And let's take first a 4i times a 12 minus 3i. If that I was a variable, let's say for instance if it was an x, what would you do? Sure, you would distribute the 4i through. So that's exactly what I'm going to do. We distribute the 4i here, distribute the 4i here. 4i times 12 is going to be a 48i. And 4i times a negative 3i is going to be a negative 12i squared. And I think we know now, as soon as you see that I squared, you think negative 1. So I'm going to put a -1 right in here, and a -12 times a -1 is going to be a +12. Now, is that in standard form? Is that mathematical model with the business in the front, the party in the back? No, we've got our business in the back and we've got our party in the front. We've got to rearrange that and put it into standard form. There we go. Now, the multiplication can get a little bit more complex. Let's say, for instance, that, let's say we've got this. Now, again, I acts like a variable until you see I squared. So if that's acting like a variable, what would you do with that? Certainly, you would FOIL it. So let's FOIL it. So a -2 times a 6 will be a -12. -2 times -2i will be a +4i. And then we've taken that -2, we sent him all the way through the second parentheses. We're done with him. Let's pick up the next guy. 5i times 6 will be a 30i. And 5i times -2i. 5 times -2 is a -10. I times I will be an I squared. And again, I squared, I think -1. So that means I'm going to put a -1 right in here. And a -10 times a -1 is a +10. So now what I'm going to do, just like I've always done, I'm going to combine up those like terms. So -12 plus a 10 will be a -2, and a 4i and a 30i will be a 34i. Can I put those two together? Well, no, that one doesn't have an I. Is it in standard form? Do we have our business in the front, party in the back? Yep, that's our standard form. So we know that we've got it. All right, one more of multiplication. And then we're going to dive into division here. Yet again, we know that when we see this, I is acting like a variable right now, so that tells us that we are going to FOIL it. So 3 times 3 will give me 9. 3 times -4i will give me a -12i. Take this guy and send him through. 4i times 3 is a +12i. And send him on in the back. +4i times -4i is a -16i times I is an I squared. And I squared -1. So I'm going to plug that -1 right in here. And -16 times -1 is going to be a +16. And I'm going to combine them by like terms. Now a 9 plus a 16 will give me a 25. But this -12i and this +12i, those will completely cancel out. So like I said before, it is possible to start with a complex number, and after the mathematical operations end with a real number. That's totally fine. But the interesting thing is, this utilizes what we call complex conjugates. We've talked about conjugates before. Recall what conjugates were. When we talked about conjugates before, we dealt with square roots. Say, for instance, we have the square root of A plus the square root of B. We said its conjugate was going to be the same two terms, just simply change the sign between. Those two were conjugates of each other. But that was conjugates when we had radicals. You can still have conjugates with complex numbers, and it's the same principle. In other words, an A plus BI, and its conjugate would be, yes, A minus BI. Those two are going to be conjugates of each other. And the cool thing about complex conjugates is what happens when you multiply them together. I need a little bit extra room, so I'm going to put that up here. Slide it up here now. The product of conjugates, complex conjugates, is a real number. Just like we had just seen, when we took that 3 plus 4i and we multiplied it to a 3 minus 4i, once we FOILed that, the result was just simply a 25. It knocked out all of the imaginary numbers. That will happen every time. Let's take these two conjugates. Let's prove that. If I have two conjugates that I'm multiplying together, like we said before, we're going to FOIL this. And so when I FOIL it, a times a will be a squared. A times negative bi will be a negative abi. Pick this one up, send it through. That will be a positive abi. And a bi times a negative bi. Positive times negative is negative. B times b is b squared. And I times I is I squared. And whoop, there's that I squared. That's a negative 1. I think at this point we know that what's going to happen when you multiply by a negative 1, you're just changing that sign. So I'm just going to change it to a b squared. And then right here in the middle, these like terms will end up canceling out. And I get an a squared plus a b squared. But the point here is that the imaginary numbers are totally gone. I have wiped them out and I came down to just a real number. So complex conjugates are very useful, just like when we did conjugates dealing with our roots and our radicals. The beauty of these conjugates, a plus square root of a plus the square root of b and the square root of a minus the square root of b, is the when I multiplied them, it got rid of the radical. Well, same thing here. When we multiply them, it gets rid of that imaginary number. So these are very useful when dividing complex numbers. Just like here, this was very useful for dividing our roots and radicals and rationalizing that denominator. This is going to be useful also for dividing complex numbers. So it's used to divide complex numbers. So in other words, let's say I have the complex number a plus bi, and I want to divide it by another complex number, c plus di. Just like when I had complex roots and radicals, and I would take this denominator and I would multiply numerator and denominator by this conjugate. Remember that process. That's the process of rationalizing a denominator. This process here allowed us to get rid of that radical that was in the denominator. Same idea here, that if I will multiply the numerator and that denominator, multiply the numerator and denominator by the conjugate. But the catch is the conjugate of which one? It's the conjugate of this denominator. By doing that, that will get that I out of the denominator. But more so, it's not so much the idea of getting the I out of the denominator. It allows us to actually do the division and taking that top complex number and dividing it by that bottom complex number. So let's see what those look like. Let's say that I have an 8 minus 2i, and I want to divide that by a 3 minus a 5i. So what I'm going to do here, in order to accomplish the division, I'm going to multiply the numerator and denominator by that conjugate, 3 plus 5i. Remembering that 3 plus 5i over 3 plus 5i, this is really just a 1. So I'm not changing this value, and this is just the method of doing that division. And you know that when you multiply fractions, you do cancel the diagonals, but nothing will cancel here. So I'm just simply going to multiply straight across, and I'm going to FOIL this. When I FOIL across the numerator, 8 times 3 is a 24. 8 times 5i is going to be a 40i. Negative 2i times 3 is a negative 6i. And a negative 2i times a 5i is a negative 10i squared. Now when I FOIL that denominator, 3 times 3 is 9. 3 times 5i is a 15i. Negative 5i times 3 is a negative 15i. And a negative 5i times a 5i is a negative 25i squared. And once again, as soon as you see I squared, think negative 1. So I'm going to turn this into a negative 1 here, and I'll turn this into a negative 1 here. But a negative 10 times a negative 1 is going to be a positive 10. And on that denominator, a negative 25 times a negative 1 will be a positive 25. But notice on the denominator, these two are going to cancel. And I expected that. I wanted that to happen. That's why I chose to multiply by the conjugate so that they would cancel out. So on my denominator, I really just have a 34. Because 9 plus 25 is 34. Now in my numerator, I'm going to combine up the like terms. A 24 and a 10 is going to be a 34. And a 40i minus a 6i will be a 34i. Now I do need to simplify this if I can. And there's a couple of ways of handling it. If you recall when we were doing the simplification of our radicals, and what I said was I was not going to distribute that through that parentheses first so that I could cancel on the outside of the parentheses. Same idea here. So what I can do now that I know how to factor, I'm going to slide this up here, is I can take that numerator and I can say, well, I can divide a 34 out of both of those. When I divide a 34 out of here, I'm left with 1. When I divide a 34 out of here, I'm left with I. And then that denominator 34 will stay there. Now on the outside here, I can cancel these. Both of them will cancel out completely, and I'm left with just that 1 plus I. That's one way to simplify it. The other way to simplify it is to say, well, this 34 will go into this 34 once, and this 34 will go into this 34 also once, leaving me with an I. But you need to be very careful about that, because if this won't divide evenly, you can't do it. You have to be very careful and make sure that it will divide evenly. Like say, for instance, that instead of a 34 plus a 34i, I have a 34 plus a 68i over a 34. Well, see, this 34 will go into here once, but it will go into there twice. So you need to make sure that it will go into both. And again, the other way to handle this is to say, well, I can factor a 34 out of both of these numerators, leaving me with 1 plus 2i, and that 34 will cancel with this 34, leaving me again with that 1, well, sorry, not there, but leaving me with that 1 plus 2i. So again, you got to be careful about it. What I've noticed over many semesters of teaching is that my little shortcut method here tends to confuse people, and so I have found over the years that it seems to make sense to people better if I do the idea of factoring out and canceling on the outside of parentheses. So I've started doing it that way. Now let's try one more, just to get really good at this before we turn it loose. And let's take a 2 minus 3i times a 5i, and I'm going to divide that by a 2 plus 3i. Now, I'm getting all excited because I'm going, well, I know that I'm going to multiply by that conjugate, but notice that numerator is pretty complicated. It's not as simple as the one that I had seen before. It's funny to say simple with a complex number, but that's a very complex number up there. So what I'm going to do before I start anything at all is I'm going to go ahead and distribute that 5i through here, trying to simplify that numerator as much as I possibly can. So when I do that, 2 times 5i will be a 10i, negative 3i times 5i will be a negative 15i squared over a 2 plus 3i. But then I'm noticing here that this I squared will be a negative 1. So I have a 10i, negative 15 times that negative 1 will end up being a positive 15 over a 2 plus 3i. Now remember, we keep talking about putting things in standard form and creating that mathematical mullet, but I'm not going to worry about that too much until the very end. Right now I'm just going to try to get this thing done, and then I'm going to turn it into the standard form at the end of the problem. So here I'm going to do the division, and in order to do the division, what I'm going to do is multiply the numerator and the denominator by the conjugate of the denominator. So the conjugate of 2 plus 3i is 2 minus 3i. And remember, yeah, when I multiply fractions, I need to cancel in the diagonals, but nothing's going to cancel. So I'm just going to go ahead and multiply across the top, and I'm going to FOIL that. When I do, 10i times 2 will be a 20i. 10i times negative 3 will be a negative 30i squared. And when I multiply inside, 15 times 2 will be a positive 30, and 15 times negative 3i is a negative 45i. Now in my denominator, when I FOIL, hopefully hopefully you guys are noticing that whenever you FOIL these conjugates, these outsides and insides will cancel, and they will cancel every time. That's why you're choosing to multiply by a conjugate, because you want them to cancel. So if you know that's going to happen and you can trust that it's going to happen, you don't have to do the full FOIL. You can just simply say that the first 2 times 2 will give me 4, and in the back 3i times a negative 3i will be a negative 9i squared. But here again, every time you see that I squared, you need to be thinking negative 1 here and negative 1 here. So now what I'm going to do is I'm going to take that negative 30 times a negative 1, and that'll give me a positive 30. And here's the rest of it. And on that denominator, same thing down here. Negative 9 times negative 1 will be a positive 9. So that in that denominator, I really just have a 13. And in my numerator, when I combine up like terms, 30 plus 30 will be 60, and 20i minus 4i will give me a 16i. Sorry, that's a 45. My apologies. It's not 16i, that's going to be a negative 25i. Let's just clean that up completely. There we go. Now, is there anything that a couple ways of handling it. I can try to divide the 13 into the 60, and it won't go. I can try to divide the 13 into the 25, and it won't go. I can also look at this and say, can I factor anything out? I can certainly divide a 5 out of these, but when I divide that 5 out, it won't cancel with the 13. So there's no point in doing that if it won't cancel. But is this that mathematical mullet? Well, kind of. But the mathematical mullet really illustrates that real part separated and the imaginary part separated. So what would the real part be? Well, the real part would be the 60 divided by that 13. And what would the imaginary part be? It would be right back here, this negative 25 over 13 and the I in the back, because it demonstrates what the B part of that imaginary part is. So there's your mathematical mullet, there's your standard form. Now again, let's say that instead of a 13, let's say you ended up with a 15 down there. So you had a 60 minus a 25i divided by 15. Now that's not what happened, but let's just say it did. Well now again, I can go ahead and divide this out, and I can divide this out, and I can say that I've got a 60 over 15 minus a 25 over 15i. 60 over 15 reduces to a 12 thirds, which actually reduces to a 4. And 25 over 15 reduces to a 5 thirds. So that would be your answer in that case. If you don't like that method, then let's factor out of the numerator. And I can take both of these and I can divide a 5 out of each one, and then 5 comes out of 60 12 times. 25 divided by 5 is a 5i. Here's that 15 in the denominator, and yet again out here on the diagonal this will cancel. 5 goes into 5 once, 5 goes into 15 3 times. I am left with a 12 minus 5i over 3. And that here's the real part, 12 over 3, like we had said before. And here's the imaginary part, that 5 over 3. And 12 over 3 still simplifies to the 4. And that's how you get that. Again, that's not the answer that you got. The answer you got over here was with the 13. I was just saying, what if it was something that actually could factor, something that actually could simplify? So, that's everything that you need to know about complex numbers. You now know how to simplify a complex number. You know how to add, subtract, multiply, and divide your complex numbers. Biggest thing that you need to remember is that whenever you have a negative underneath the square root, take that I out of there immediately and then deal with the square root. The other thing that you need to remember is I acts like a variable until you see I squared. When you see I squared, what's the result? A negative 1. You substitute a negative 1 in there. Otherwise, it's same old stuff as before. And so hopefully this will make some sense to you, and that's everything you need to know out of section 1.4. So, all in favor of leaving, say aye. Aye. Have a good day, folks.